Hey everyone. Am I audible? Hello? Hello? Am I audible? Good morning everyone. Okay. Okay. Not able to find my hard disk. Where to come corner? Triggering the big girders, like I think this is over, the bending moments and the shear forces over here. Section also we had done, and have we done this shear capacity, check for shear capacity and the check for shear buckling of web using simple post-critical method? Have we done this? Check for shear buckling of web using simple post-critical method. I'm audible. Is it over here? No. Check for shear buckling of web using simple post-critical method. It's over here. This part, step number 7 is over. For sure. Check for sure. Moment is done. Check for moment capacity of flange. Then we have the check for shear capacity. Then we will need the IS production. हेलो रुको तो हम तो वो क्लास के बाद फोन कर रहे हैं we have done the shear capacity. Now we will do this. So this one we have calculated that when we have done with this design shear strength, we have calculated and that we have found that this is greater than our the shear which was calculated due to the this one due to the loadings. Whatever shear was calculated, that was your 996 kilonewton, and therefore since our design shear is greater, so it is okay. Yeah, next we have the check for shear buckling of web using simple post-critical method. So for that again you have to go to your IS code, this one, IS code page number 59 here, IS 800. Page number 59, clause number 8.4.4.4. This one, this one. Okay, simple post-critical method. We have this one, the nominal shear strength Vn of webs with or without intermediate stiffeners as governed by buckling may be evaluated using one of the following methods, which is simple post-critical method, either this or we have the tension field method, but we will do now with the simple post critical method. Here the simple post critical method based on the shear buckling strength can be used for webs of I section girders with or without intermediate transverse stiffeners, provided that the web has transverse stiffeners at the supports. Okay, the nominal shear strength is given by this Vn is equal to VCR. So what is our VCR? We know our VCR is how much? AV tau B, AV into tau B. Okay, but to find out AV, we know AV is the shear, and in an I section, your web always carries the shear, so it will be nothing but the shear area will be how much? The shear area will be the area of the web here. Then we have tau b. Tau b is what? Tau b. Only the left portion is how much? To find out the shear force corresponding to web buckling VCR, you have to know what is tau b and what is tau b. Tau b, your tau b value, which is the shear stress corresponding to web buckling, determined is as follows. That means your tau b is based. Your formula to find out tau b is based upon the lambda w value. Now if your lambda w is less than equal to 0.8, then you will follow this formula, which is tau b is equal to fy by root 3. When your tau lambda w is between 0.8 to 1.2, your tau b is this much. Okay, and when your lambda w is greater than 1.2, then your tau b is this much. You need to follow this. So now if we see our this one, what is our Vn is equal to AV into tau b. AV into we have to find out Vn, and Vn is AV into tau b. Now what is our tau b? Okay, one more thing. This one. Let me tell you here, like we have to find out this lambda w. Now to find out lambda w, you have to find out which is lambda w is what? Lambda w is the non-dimensional web slenderness ratio for shear buckling stress given by lambda w is given by fy root over fy by root 3 tau cr value. Now we know for to find out lambda w, we know fy, what is our fy, but we don't know what is our tau cr value, which is the elastic critical shear stress here. So now to find out this, you have to know this values. The elastic critical shear stress of the web is given by kv pi square into E by 12 whole into 1 minus mu square into d by tw whole square. Okay, where we have our mu is Poisson's ratio we know, then Kv value. This Kv value is 5.35 when stiff transverse stiffeners are provided only at the supports. That means we don't have intermediate stiffeners here at the center of a I on the webs of a I section. Okay, so we know this DTW, we already know all those things we know. So we will first of all, since you can see here, to find out the value of VCR, which is Vn, to find out this value, ultimately you have to find out first of all this tau CR value, which is the elastic critical shear stress, because once you calculate this value, then only you can calculate the tau lambda W. Once you find out lambda W, you can calculate the tau B value. Once you calculate tau B value, you can calculate your VCR, which is the shear force corresponding to the web buckling. Okay, so you will have what here? Now we will find out the value of, first of all, we'll find out the value of here, this one, tau C. Okay, so first of all, we are going to find out the value of tau C. So tau C R critical, this one was how much? Kv pi square by 12, 1 minus mu square whole into d by dw. Okay, so now once we have values, Kv is how much? 5.35, right? This one, 5.35. Array where it is 5.35 for when we have no intermediate stiffeners. Then in the IS code it is already mentioned here, this one 5.35 kV value. Then we have pi square, pi we know, e we know, 20 10 to the power 5, 12 into 1 minus mu square, mu is 0.3 we know, d by dw, d we had this I section, we had this I section, and this one was how much? This one was 1400. This one was 1400, and this thickness, this was 12. So 1400, this 1400, this 1400 into 12. This is our D 1400, this one, and TW, the thickness of the web is 12. Okay, so we have got our tau CR value. Now, once we know tau CR value, this tau CR value, we can find out, we can place this value of tau CR and find out the lambda W. So, what is our lambda W value now? Lambda W is root over Fy by root 3 tau CR. So, Fy is, we know it is 250 root 3, and tau CR is how much? Tau CR we have calculated to be 71.04. So, it is 1.425 greater, which is greater than 1.2. Why? Because we have calculated the lambda W value, which is how much? 1.425, this one. So now we have to check where this lambda W lies, such that we can find out the tau B value. So our lambda B is how much? 1.425, which is, this is not following. Lambda W is not less than 0.8. Lambda W is also not between 0.8 to 1.2, but our lambda W is greater than 1.2, right? So that means our this condition is following. This third number condition is following, which is tau B is equal to Fy by root 3 lambda W square. So tau B we will find out now. We can easily, now we can find out, because we know we have to take this formula and then we can find out our tau B. So tau B we will find out now, this one, tau B, because we have got the lambda W to be greater than 1.2. So tau B is Fy W by root 3 gamma mw, root 3 gamma mw. So sorry, lambda W. So Fy is 250 root 3. Lambda W value, we know this one is our lambda W value, which we have calculated. So we have got our tau B value. Now once we got our tau B value, from the IS code here, tau B value we have got. Now we can easily find out our VCR, shear force corresponding to the buckling, which is nothing but your Vn, which is nothing but your Vn. The nominal shear strength is given by this VCR. Vn is equal to Vcr. So once you got your lambda b, you can find out your Vcr is equal to Vn is equal to Av tau b. So Vn is how much? Av, this is your Av into this one, tau b. So tau b is the 71.08 tau b value. So we have got our shear area, we know, because why shear always occurs on the web? Your web always carries the shear, resists the shear, and your flanges always resist the moment. So this is the shear area which is resisting the shear. So we have how much? This one. Area of the shear area is how much? 1400 into 12. The web area. This one. Area 1400 into 12. This is the area. Okay. Now we have this one. So into tau b, and then we got how much? Our Vn is this much, which is 1194 kilonewton, which is again greater than our 996 kilonewton, which is the shear force due to the loads which are coming, right? So therefore it is, our design is okay. Fine, this was the check for your shear buckling, okay, of web using the simple post critical method. Okay. Also here one more thing, when we have uh, some things are to be noted here. Since this is greater, our shear buckling is also greater than the shear due to the applied load. Hence, our strength of the web is greater than the applied shear. Okay, hence our strength is greater than this applied shear. Now, if sometimes what will happen? This is our VCR, right? VCR, or you can say the VN, the nominal shear strength. So if this is greater, sometimes this is greater, so it is okay. But if sometimes this value, VCR value or VN value is less than your shear strength, this shear strength due to the loading, what will happen then? Then the buckling strength is required to be improved. Okay, by changing, we will change the web section, or it should be designed using tension field actions. Okay, so when this is less, what we'll do, we will either, we have to change the uh, web section. Okay, that means the section which we have considered, this web section which we have considered is not okay, because we had assumed this thickness, right? And the this thing, the depth we had assumed, so we have to change this things. Thickness we can either increase, and or this one we can increase, and then we'll again check it, we'll take a different web section, and then such that your critical this shear, nominal shear strength should be greater than your shear strength which is due to the loadings. Okay. Mm. So till here we have calculated the web buckling, etc. Okay. So we'll do the design of the thing. It's till here it's okay. We'll do till here the shears. Buckling we'll do till here. We'll check the shears. Okay. And the design of the load stiffeners at the supports we'll do later. Okay, because I'm not having the particular notes now here. I'll not be able to show you. So we'll do later that thing, the design of the uh load carrying stiffeners on the supports. So we'll do later because I'm not having. Not control the shared content until you stop. I was annotating. Okay. So me take your attendance. In the next class, we'll go with the tanks because I have to check. I don't know, my hard disk is not working, and all the files and the this notes are there. I hope I don't lost them. Today's second 11. Roll number 44. 44. 44. Then we have 64. 65.
Yes, ma'am.
65. 67. 69. 70. 72.
Present, ma'am.
73.
73, ma'am.
74.
Present, ma'am. 74.
75.
Yes, ma'am. 75.
76. 77. 78. 81. Lobsang. 82. 83.
Present, ma'am. 83 present.
Okay, 84.
84, present, ma'am.
85. 86. 88. Abu Talib Siddiqui. 89. Okay. 89. 91. 92. 93.
Present, ma'am.
94. 95.
Present, ma'am.
95.
Yes, ma'am. 95.
96.
Yes, ma'am. 96.
97. 98.
8 present, ma'am.
99. 100. 100. 1. 102. 110.
110.
112. 115.
115 present, ma'am.
116. 116.
110.
117. 119. 121. 122. 123.
Yes.
23.
22.
22. 23.
22, miss.
Okay. Under 25. 126. 127. 128.
Present,
130.
ma'am.
128.
Yes, ma'am.
130. 132. 135. 137. 139.
137, ma'am.
137.
7.
139. 140. 142. 147. Integrated 1. 2. Hello.
Hello, ma'am. Michael present.
Okay. 2. Tashika. Lashram.
Present, ma'am.
Dawson.
Present, ma'am.
Ma'am.
Hmm.
77, ma'am. Present.
77 present. 110. Some of them are giving in chat. 110. 69. I'll give the absentees roll numbers in the group. Okay, once you check, if I missed out someone, you can inform me. And in the we have class at 1 now. Okay, we'll meet at 1. Okay.